Swayam Prabha, Digital India, Educated India.
So today's lecture is basically introduction to field effect transistor. So in last classes we have discussed about the PN junction, bipolar junction transistor, and we also discussed about metal semiconductor junction. So Schottky diode, ohmic contact, those things we have discussed. Now when we discuss junction field effect transistor, here the mechanism is basically the field effect. So by applying a field, we are controlling the channel, right? So there are multiple variations are available in the literature. Some of them will discuss briefly. Then we will go to MOSFET, and an important constituent of the MOSFET is the MOS, metal oxide semiconductor. It acts like a capacitor, right? So MOS capacitor is a very important constituent. Unlike metal semiconductor contact, here we have a small thin oxide layer, right? So metal is not directly connected to the semiconductor here, but it is connected via one insulating layer, silicon oxide, or it can be also called metal insulator semiconductor, and then you can have field effect transistor. So it can be any other insulator also. So first let us discuss about the junction field effect transistor. Now all of you know that if you have a PN junction and you reverse bias it, what will happen? The depletion width will increase. So by applying a reverse bias across a PN junction, you can control the width of this channel, right? Now this is P plus gate, this is also P plus gate. So the purpose here is that if you have P plus here, that means most of the depletion region will be extending in the N region, right? Now both are identically doped, so P plus and this P plus are same. So that means both sides the depletion width will be same for a given or applied voltage. Now in this case, we will only apply the reverse bias, right? So that means your VG has to be less than 0. Correct? If you apply positive gate bias, then of course this diode will turn on and it will not serve the purpose. So the applied gate voltage in this case will be negative only. And then there are two contacts at the end of this N type silicon or N channel. One is called source, other is called drain. Now source name is coming from source is basically sending the carriers, right? So what are the carriers here? Electron, right? So electron will move from source to drain. That means your drain voltage has to be positive. So what we will apply a VDS voltage. A positive VDS will be applied in this case. Now, if you closely look at the conduction mechanism for a given gate voltage, right? For a given gate voltage, voltage from source to drain is changing, right? So that means now the voltage here is Vs, voltage here is, let's say, Vd, the drain voltage, and this is source voltage. Now this voltage will change gradually, right? And that is also has a name, gradual channel approximation. So in gradual channel approximation, this voltage is basically changing slowly, is not abruptly changing. So along this channel, if you move certain distance, this voltage is basically increasing, right? Now if the voltage on N side increases, what will happen to the reverse bias? It will be more reverse bias, right? So that means the depletion width will be more here, right? So you can see something like this, depletion width is increasing here, right? Now if you apply a small VDS voltage, then the change in depletion can be ignored, right? And you can have almost a uniform channel, right? So this is basically along this is x axis. You can this is x equal to 0 to some x equal to L. L is a channel length. So 0 to L. This voltage is changing from 0 to VD or VS to VDS. Correct. Now, if you want to find out the IV characteristic, then the resistance, if your VD is less, right, this channel is wide open, right, for given gate voltage. For given gate voltage, if your VD is less, this is wide open, right? So that means the conductivity of the channel will be more. What will be the maximum conductivity? If this length is, let's say 2A, and the width inside the paper is Z, right? What will be the maximum conductivity? Rho L by A, right? And what is the cross section area? 2A times Z. So the minimum, this will be minimum resistance, right? Because the channel is widest here. So the minimum resistance will be rho L by the width of this channel 2A. We are the reason we are choosing 2A because it's identical, so we can just have A upper side and A lower side, right? So that will be 2A. 2A times Z. Z is the thickness inside, right? So it's basically the width of the channel inside the paper. So that we are not controlling. We are only controlling along this 2A. So this height will reduce by will be less than 2A when you apply a reverse bias. Okay. So for a small drain voltage, this change is small, and you can say the resistance is constant or conductivity is constant. So you will have linear characteristic here. Then as you increase, you reach near the pinch off. This the voltage, the drain and gate voltage will be such that your depletion width W, so this is W, will be equal to A, right? So that will be pinch off, right? So up to pinch off, basically, you know, if you apply the voltage, current is increasing. Beyond pinch off, this current become constant. Of course, there will be a secondary mechanism, especially in case of short channel diodes. This length will be less, right? So resistance will decrease and current will increase. So that is short channel effect or secondary effect. Otherwise, for long channel, the current will be constant beyond pinch off. Now, what happens beyond pinch off? There is no channel here. So that means it's a depletion region, right? So that means the field is there. There are no carriers to say in this region, but this carrier can move through this depletion region due to the applied field. And if you want to drive the equation, let's say W is the depletion width, and it is a function of voltage. So at position X, the voltage is, let's say, Vx. So at X equal to 0, if source is grounded, the voltage will be 0. At the end, X equal to L, voltage will be Vd or VDS, you can say. So depletion width, you can recall this expression, 2 epsilon Vy Qn, right? Where N is the doping of less doped side. So here less doped is N side, right? So it's Nd. For one-sided junction, this is the expression for depletion width. And of course, if you see exact action, there is VBI minus VGD, right? But this is large compared to VBI, so you can just simply write VGD. Now, the voltage at which this depletion width is equal to A, right? We call it pinch off voltage, right? So V pinch off can be obtained from here. V pinch off will be A square QND by 2 epsilon, right? So A square QND by 2 epsilon will be V pinch off. And V pinch off is what? Minus VGD, right? So that is VD minus VG. So this is a pinch off voltage. So what will happen for a given gate voltage? For a given gate voltage, if you increase the drain voltage, right? So it will increase initially, but once it reaches V pinch off, right, it will become constant. So if you want to get the expression for current, so you can consider element at distance x, element of length dx. So the resistance of this element will be rho times dx divided by area of cross section. Area of cross section is what? Z is inside the paper times this a minus w. This is also a minus w. So 2 times a minus w times 2, and this is z, right? And this a minus w is written as h here, right? So you can write h 2hz, and then I will be this is resistance, right? So your dB will be I times this is small resistance. So I can be written as dB by dx 2zh by rho, and then you can integrate it from 0 to L. Now you can notice one more thing here. V pinch off is Vd minus Vg. Now pinch off will occur when gate voltage is negative, right? So that means your Vp will be positive for N channel, and it will be negative for P channel. Please interrupt me if you don't understand. Right? Now this A minus W you can write. W is basically this thing. So if you substitute A here, and A you can write in terms of Vp, right? So if you substitute here A minus W, now W can be written as 2 epsilon by Q and D. 2 epsilon by Q and D will be A by root Vp, right? A by root Vp times minus Vgd, correct? This is root 2 epsilon by Q and D. 2 epsilon by Q and D will be A by root Vp, correct? So then you substitute it here, right, and integrate. So 2z by rho 1 minus. Now this is basically for L. For any position x, instead of Vd you can write Vx, right? So it becomes Vx minus Vg, right? So here Vx minus Vb square root. And then if you integrate it, you will get a slightly complicated expression like this. Where G0 is given by, okay, you can basically see here, if you compare this one, G0 will be your 2ZA by rho L, right? 2ZA by rho L. It's a maximum, sorry, we have maximum conductance or the minimum resistance. So now it will increase only up to when there is no pinch off. Once pinch off occurs, that value will be fixed. So at pinch off, your Vd minus Vg equal to Vp, and if you substitute it here, this Vd by Vp, this Vg can be written as this is Vg. Vd can be written as Vg plus Vp, right? So Vg by Vp plus 1, and then this Vd equal to Vp, Vd minus Vg equal to Vp. This will be 1, right? So 2 by 3. So 1 minus 2 by 3 will be 1 by 3, and then this is Vg by Vp. So you will get a simplified expression like this. But this is for saturation current. Now experimentally, what is found? It obeys a square law, where IDSS is the saturation current with Vg equal to 0, right? So if Vg equal to 0, what do you get here? G0 Vp by 3, right? So that will be your IDSS. This is ID saturation is basically IDSS times 1 plus Vg by Vp square. So this is a typical IV characteristic of junction field effect transistors. Okay, and we obtain it basically by changing the depletion width. Now this is again a PN junction. There will be problem of charge storage. It will its turn on, turn off time will be influenced by the charge storage. So there is a better option. Instead of using a PN junction, we can use a metal semiconductor junction only directly, right? So this also acts like a diode, but this is charge storage issue is less here. It is much faster. So the device based on this phenomenon is called MESFET, metal semiconductor field effect transistor. So here metal is directly connected to the semiconductor. So what is done here? A high resistivity, right? A high resistivity, resistance or resistivity. Wafer is taken, right? Substrate is taken. We also call it semi-insulating wafer. So the purpose is basically it is used to isolate the different devices that are there on the same substrate because the conductivity is very less. Then a thin layer is epitaxially grown, right? Later people use implantation also, but very thin layer, so that by depletion region you can cover almost all the layers, so that channel is blocked. And then metal is deposited. So this metal semiconductor junction again, if this is N type, so you have to, for depletion region, which voltage you have to apply? It will be forward bias if metal is positive, right? So you have to apply negative voltage for it to deplete, because negative voltage will push the electron away, right? So then there will be depletion region here. So you can control the channel width. Now, what we want the channel to have high conductivity. So high conductivity can be increased by increasing the doping, right? So if you increase the doping, the conductivity of the channel will increase, but it will also increase the impurity scattering, right? So people use a variation of this type of field effect transistor. They call it modulation doped or high electron mobility transistor. Now what is done here? Instead of using a simple layer like this, a heterostructure is used. So let's say this may be your contact, this may be your gate, and you have this high band gap material and a low band gap material. So this high band gap material is actually doped, and low band gap material is not doped, but it has a, you can think like this, it has a smaller band gap. So these electrons will have tendency to go to this quantum well, the well that is formed by low band gap material. So now donors are here, but the carriers are here. So when these carriers move, they will not experience the scattering, right? So their mobility will be even higher. And if you look carefully, let's say this is also N type, this is also N type, and when in equilibrium, what will happen? These Fermi levels should align. So when these Fermi level align, so this has to basically kind of go up, this go down. So you will basically get this kind of band structure. So this is gallium arsenide, this is algas. Algas has of course higher band gap. And then there's some composition used, X, 1 minus X, right? And this kind of a quantum well is formed where these electrons are confined. And this is also called a two-dimensional electron gas. Now, why two-dimensional electron gas? Because the density of electron is quite high, 10 to the 12 per cubic centimeter. Eh? Please note the unit. It is not per cubic centimeter, it is per square centimeter. And the layer thickness is quite small, order of few tens of angstrom. So these electrons that are here, two-dimensional electron gas, they will have high mobility because there is practically no scattering from ionized impurities. And this technique is called modulation doping. And such structures are called high electron mobility transistor or MOSFET, or sometimes called separately doped field effect transistors, right? And they achieve high electron mobility or high conductivity. Okay, any doubt? Now we know that the mobility depends on the electric field, right? So for a small electric field, mobility is constant. But if you keep on increasing the electric field, mobility will not remain constant. Rather, there will be some saturation velocity. And once you achieve the saturation velocity, that means mobility has to go down, right? So that at higher fields, drift velocity is limited by the saturation velocity. And this phenomenon is called short channel effect. So it can be achieved in number of ways. First is, of course, when you operate at high field, your velocity is saturation velocity. Now, in that case, your current will be, because the velocity is no more mu e, it's a Vs, right? So current will be simply Qn times velocity times area of cross section. At saturation velocity, this will be your current. And when your channel length is small, right? That time also, due to pinch off, this change in length will be significant, right? Because the pinch off moves from x equal to L to inside at a smaller x, then the current will basically increase, right? Because effective channel length is reduced, rho L by A, right? So this L is reduced, so resistance has decreased, right? So that will also cause increase in current. So that is also called that also comes under short channel effect. So what is done basically, instead of using V equal to mu E, a more generalized expression is used. V equal to mu E by 1 plus mu E by Vs. So instead of having a discontinuity here, as you see in piecewise linear model, we have a more smooth curve here. So typically this kind of parameter is used to calculate the drift velocity. So if the field is small, then you can ignore this one and your Vd will be mu E. If field is large, then you can ignore one, your drift velocity will be Vs. But most of the device, they actually operate, somewhere here, right? So you cannot keep on switching these regions. So we use this generalized expression. Now we will go to MOS capacitor. Now what will be there? We connect the metal semiconductor with a thin insulating layer. Its structure is very similar to a capacitor, right? Where we have two metal plates and a dielectric. So this oxide is or insulator is a dielectric, and then metal on one side, semiconductor on other side. Now the difference between metal and semiconductor will be metal respond very fast to the voltage. So that means whatever charge is there, it will be exactly at the interface, whether positive charge or negative charge. It will be positioned at the metal dielectric interface. But in case of semiconductor, there is doping here. So what will happen? This charge will be kind of distributed. So there will be a field inside the semiconductor. Inside metal, you cannot have field. So E is 0 inside the metal. But in semiconductor, you can have a field. So that makes the analysis of MOS capacitor interesting. So before we analyze the MOS capacitor, let us see their Venn diagram. So this is ideal, metal, then insulator and semiconductor. So in metal, of course, you have work function Q phi m. This is the metal Fermi level. Then you have oxide or insulator here. And then this oxide also have some kind of conduction balancement, but it's insulator basically. So it's quite high basically. So this barrier is called Q phi b. And this of course is a vacuum level. And then electron affinity Q chi for the semiconductor. band gap is Eg, and if it's n-type doped, the difference between Fermi level and intensity level is called Q psi b. And if it is p-type, then the difference between Fermi level and intensity level will be between this Q psi b. This will be called Q psi b, right? So between p-type and n-type, their sign will be different, and either the sign will be different, or you can define them in different ways, right? So if you want to find out what is the difference between the two Fermi level, phi m and phi s, so phi ms will be phi m minus phi s. Now what will be phi s here? Q psi plus Eg by 2 minus Q psi, right? Now phi, chi and psi, they are the unit of voltage, and Eg is the unit of energy, right? So if you want to be consistent with the unit, then instead of Eg by 2, we will use Eg by 2Q, so that it has a unit of potential. Same thing you can write for p-type. So please modify this expression for p-type and show me how phi ms will look like for p-type. So for p-type, phi ms will be phi m minus Q times psi plus Eg by 2, right? Now what is will happen? Plus Q psi or minus Q psi? So this is minus Q psi because it's going up. This will be plus Q psi. So plus psi b, you can psi b bulk, right? So this is a doping coming from the bulk. And can you relate this psi b with carrier concentration? So here n will be Ni exponential EF minus EI by KT, right? So this is Q psi b by KT. And what about P concentration here? Again, Ni exponential EF minus EI by KT. So minus Q psi b by KT. Now this is for N type. For P type, signs will change, right? Because this will be psi b now. You can see in next slide here. This is for P type. So now this is Q psi b. So here P type will be exponential Q psi b by KT. So please be careful about the how you define Q psi b. Okay. Now what will happen? Let's again consider N type. In case of accumulation, how will you achieve the accumulation? The gate will be positively biased or negatively biased? For accumulation, what will you do? You will apply a positive voltage here or negative voltage here. Now accumulation means you have to get the electrons here, right? So these electrons in the bulk, they should come to the surface. Now they will come to the surface when you apply a positive voltage here. Now by applying the positive voltage, what will happen to the Fermi level? It will go up or go down. Now voltage is positive, that is energy is minus QB, negative, right? So this Fermi level will actually go down. So basically you will have some kind of this thing here and this thing here, right? Correct. And same thing you can have for P type. So for N type, you apply positive voltage, Fermi level goes down, and because this is positive, this is negative, so this will be the direction of field. So in the direction of field, potential decreases. So minus QB energy increases, right? So you see energy is increasing in both the cases, and because this is coming down, so the gap between the Fermi level and EC is decreasing, so electrons are accumulating here. In case of P type, you apply a negative voltage, right? So that means Fermi level goes up, so it goes down like this, and here this valence band edge is coming near to the Fermi level, so holes are accumulating here. Same thing, similarly you can analyze the depletion region. So for depletion region, what will you do? For P type, you have to push away the holes. So you will apply positive voltage. So by positive voltage, this will go down. So you will have structure similar to this, but now because Fermi level is here, so there will be less concentration of holes. You can see here. So for depletion, you are applying a positive voltage to P type, a negative voltage to N type. So this has gone down. So you see that this thing here, the direction of the field here, direction of field will be opposite, and this Fermi level and the valence band edge is the separation is more here. So holes are reduced here. So it becomes a depletion. Now, if EF is closer to EI, right? That means it's a depletion region because it is depleted of majority carriers. Now, if you go ahead further and you apply voltage beyond the depletion region. So, for example, for N type, you apply a negative voltage, right? Let's say we increase this voltage further, right? So let's say this is -1 volt. You apply -2, -3 like this. So what will happen? This band bending will be even more, right? And it is possible that this Fermi level may go above EI, may go above EF, right? So this is basically your bit N type because EF is above, and here it will become P type. Now it is not that semiconductor has turned into P type, but holes are created here due to this high applied negative bias here. Similarly, in P type, due to this high positive bias, this intensity level goes even further down, right? So instead of holes here, you have electrons here, right? So these electrons are created here. Now this phenomena is called inversion. So when you apply a very high voltage beyond depletion, you can get inversion. Now there is a definition for this one. What is happening when you are applying the voltage? These bands are bending. So let's say this EC, EB, and EI are following the same route basically. The change in EC, EB, and EI will be same at particular position because their relative position don't change. The relative position of EC, EB, and EI they don't change. What is changing? Their relative position with respect to EF. So what we are concerned with the surface. So at surface, if your EF at surface is equal to EF at bulk, right? This condition is called flat band. But that means no band bending. If EF, sorry, EI at the bulk and surface they are equal, there is no band bending because EF will be constant when there is no current flow. So even if you apply the bias, because of this oxide, current is not flowing, so EF will be constant, at least within the semiconductor region. Other bands EC, EB, and EI are bending to take care of the induced electric field. So if EI at the surface, you can also use EC or EB also here because they follow the same trend. So if EI at the surface is same as EI in the bulk, this condition is called flat band. If EI is equal EI at the surface is equal to EF in the bulk, so EI at surface is equal to EF in the bulk, that means depletion region. So EI at surface is equal to EF in bulk, right? So that is basically depletion region. because the here monetary carrier concentration is same as intrinsic concentration. So it is of course more than the bulk monetary carrier concentration, and it is equal to intrinsic carrier concentration. If EI at surface is less than EI in bulk by same amount, this is psi b, q psi b, right? So this is also q psi b. Then this is called inversion, because now in this case monetary carrier concentration here is same as the majority carrier concentration in the bulk. Okay? So that's how it is defined basically. So you can see a bigger picture here. This is the bulk and this is surface. So due to apply bias, these bends are bending, and the way we define the potential here is q psi is basically the amount by which EI is bending, and amount of bending at the surface we define surface potential. So the bending at the surface is q psi s, and psi s is called surface potential. Now, of course, you can try to solve for Poisson equation. So I give you homework now. So try to solve the Poisson equation here. You can take the help of your textbook to solve for the surface potential, and surface potential is of course related to the field here. So you can get the field here, and the charge will be epsilon times E, the field. So you can basically estimate the charge concentration here. So try to solve the Poisson equation and calculate the charge concentration at the surface. So that is your homework. So please try it. Then next class we will continue our discussion on MOS capacitor, and we will venture into MOSFET. Okay. So I will close here. If you have any question, you can ask me.